This video is about parallel resistance. Now before we get into a parallel circuit, let's take a look at this simple series circuit. So we have a 10 volt supply with a 20 ohm resistor. So using Ohm's law, we can determine that the current through this circuit is the voltage divided by the resistance, which is of course 10 volts divided by 20 ohms, which is 0.500 amperes. Okay. So now remember, this is a series circuit, so if we were to put the current meter here, or put the current meter here, or put the current meter here, and any of those places, or even down here, we're going to be reading that resistance. Alright, so let's consider we have two of these circuits. So each circuit here we have So for each one of these circuits, if we were to put a current meter, we would have half an amp flowing into this 20 ohm resistor. Okay. So what does that mean about the power supply? Well, that means that this power supply is outputting half an amp, and this power supply is outputting half an amp, right? And so if we think about power, power is defined as voltage times the current. So the power for this circuit here is 10 times 1/2 is going to be 5 watts. And the power for this circuit over here is 5 watts. What's that mean? It means that the power supply is supplying 5 watts and the resistor is using that 5 watts. Okay, so remember, the resistors basically take that energy being supplied and convert that into thermal or heat energy. So what happens then if we take those two resistors, and so they both still have 10 volts. Remember, this is a node up here. All of this is the same node, and all of this is the same node. So that means there's 10 volts across these resistors. So we've already determined that if there's 10 volts, then we're going to have half an amp flowing through this resistor, and resistor R1 also has 10 volts across it. It's 20 ohms, so it's going to have half an amp flowing through it. So what does that mean? It means now that this power supply has to provide enough current to come over here and let half of that current go down this way and the other half go down this way. So this, if we were to put a current meter in series right here at the power supply, we would be reading 1 amp. So again, if we're going to put that in Blackboard with 3 significant digits, it would be 1.00 amps. All right, which means also that if we were supposed to put the current meter down here, it would be reading 1 amp. 1 ampere. And if we were supposed to put the meter in at this point, right, this point only has half an ampere flowing through it. So at this node right here, this wire, so the wire coming down has half an amp through it, and the wire over here is going to have half an ampere through it. Alright, so if we put the meter in here or here, So if we were to put the meter in at either of these spots, we're going to be reading half an ampere. But if we put the meter here at this point, it's going to be reading, it's going to be reading 1.00 amperes. Okay, so these two resistors are said to be in parallel because they have the same node here. This is all one node. This top wire is all one node, and the bottom wire is all one node. So the voltage, if we were to measure the voltage anywhere along here, we are reading a voltage of 10 volts. So these two resistors have the same voltage across them. And since they're of equal value, they also have the same amount of current flowing through them, right? Because Ohm's law tells us that the current is the voltage divided by the current. But what about the power supply? All right, the power supply over here is got to output 1 ampere because it's got to provide enough current so that we get 1/2 of an amp through the 20 ohm and 1/2 through the other 20 ohm. So if we were to calculate the total resistance, R total, we could use Ohm's law and we would take E divided by the current coming out of the power supply, which is 1 ampere. So we'd have 10 volts divided by 1 ampere gives us a total resistance of not 20 ohms, not 40 ohms, but of simply 10 ohms. Okay, so look at this. We have two 20 ohm resistors in parallel, and the result is one resistor of 10 ohms. So the equivalent circuit here would be the 10 volt battery feeding a 10 ohm resistor. Not a 20 ohm, not a 40 ohm, but a 10 ohm resistor. So resistors in parallel result in less resistance than the total in there. So the actual equation for that is a reciprocal type of equation. So we have R total for a parallel circuit. Okay, this is for parallel. We have that 1 over R1 plus 1 over R2, and if you have more resistors, it would be 1 over R3 and 1 over R4, etc. Okay, so this is the general equation for resistors in parallel. Now, there's a special case if you just have two resistors. So this case only works if you have two parallel resistors, as we do up above. All right, and so R total for parallel, and I'll put like 2 bars, parallel lines here to indicate parallel. We get just the 1 over R1 plus 1 over R2. And if you simplify this equation, you end up getting R1 times R2 divided by R1 plus R2. Okay. So this is a simplified version of this. This is the true equation. This works for any number of parallel resistors, but this lower one works specifically if there's only 2 resistors. Now if we look at this specialized one, and let's say that R1 is equal to R2, okay, Okay, so R1 and R2 were equal, then that would give us, say, R1 times R1 divided by 2R1. Okay, and so the 1R1s will cancel, so if the resistors are equal, we get a special case of R1 divided by 2, which is exactly what we have up here, right? We had 2 resistors of 20 ohms, which gave us a resulting resistance of 10 ohms, right? So 20 ohms divided by 2 gives us 20 ohms. Now this, even though I used a specialized 2 resistor case to show this, okay, if you have multiple resistors in parallel that are all the same equal resistance, you can then find R total to be this R same resistor if they're all the same. If they are all the same, then the total resistance, you just divide it by the number of resistors you have. So let's take a look here at this. So we've got 3 resistors. They're all 20 ohms. So as we've already discussed, right, we're applying 10 volts. So I'm going to have half an ampere through each one of these resistors. Okay. So we're going to have half an ampere through each one of these resistors. So given that, this power supply is going to have to feed out 1.5 amperes. Right. And so if we were to measure the current right here, we would have 1.5 amp. If we measured the current right here, we would have half an amp. If we were to measure the current right here, we're going to measure 1 amp. Okay, so at this node right here, call this A. So at A, even though they're all the same voltage, this whole line all along here has 10 volts on it, but depending on which wire you look at, there's different current flowing through the wire. So the wire connected to the source has 1.5 ampere. The wire coming straight down into R1 only has half an amp, and the wire going to the right of letter A has 1 amp. Now if we look here, call this point B. So at point B here, coming into point B, we have 1 amp. If we look to the right of point B, we're going to have our half an ampere. And if we look straight down from point B, we're going to have half an ampere. Right. So looking at resistor R3, right, we have half an ampere running through resistor R3. So if we measure the current here, we're going to have half an ampere. If we measure the current right here below R2, again, half an ampere. But if we measure the current here, at this to the left of, call this point C, this is going to have 1 amp in it. And if we call this point D here, okay, so we have below R1, we have, of course, there's half an ampere coming down through here. But at point D, to the left of point D, now we're back to 1.5 ampere. All right, so if we look at power, let's take a look at power. We know that power is voltage times current. So the power supply here has 10 volts with 1.5 amperes, which means it's using 15 watts. Okay, so be 15.0 watts. All right, so the power supply is dishing out 15 watts. Where are those watts going? Well, we have here for this resistor, we have 10 volts times half an ampere. So this one is using 5 watts. And this one is using 5 watts. And this resistor over here is using 5 watts. Okay. All right, so if you look at the power, all right, the power being supplied is 15 watts. The power being used is 15 watts. So it doesn't matter whether they're in parallel or series. When you are looking for total power in the circuit is the supply voltage, we'll call it E for electromotive force, the total electromotive force applied times the current. All right, but that's also equal to the power in each resistor all added up. It doesn't matter whether those resistors are in series, parallel, or some series parallel combination. You can always just add the power up because this is the power being used in the circuit. Okay. So it doesn't matter how many of these that we have.